There, recording. Okay, so for those of you that are here, got your quiz 1 back. If you don't have it back, they're sorted by last name. I'll combine them into one file here, alphabetically, so you can grab it there. It's yours to keep, treasure forever. It will be good for studying for the final exam, right? And so that's why I tried to write little notes instead of posting solutions, right? Because there's relatively few of you in this class. I thought, you know what? I'll just write you guys all little personalized solutions, right? Where you need them. So great job on quiz number 1. Okay. I did notice that there was a bimodal distribution in the grades, right? Some were very, very high and some were not so high, right? Kind of 2 distinct groups. And so that's fine. It's okay, right? If your grade wasn't as good as you were hoping for, that's totally fine. Right? Maybe review those notes that I left and make sure that you could redo the quiz and do well a second time. I'm not letting you do that because that's crazy. Instead, right, if you do better on the final exam, right, I'll just forget we wrote this quiz and put the weight on the final exam. Okay, and I do that for all the quizzes, right? It's always best to just write them, right? Even if, you know, you're having a bad day, you didn't study, blah, 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 right? It doesn't matter. I want you to write the quiz because then you'll have seen these questions in a test environment and you can go back and you can think, oh, where was I struggling with this, right? Where did I stumble in the test scenario, right? And then you'll be able to learn from that, take it to the final exam. I know it weighs off right now. And then knock it out of the park on the final exam, okay? And so you'll see those questions again, for the most part, on the final exam, of course. That's basically why I do the quizzes, yeah.
Will our final be animal themed?
Yes. So I like to do these animal themes. I always start with a manatee because I think they're just so cute. And for some reason, all my animals start with M. So I can't decide which one, except I have a platypus themed test that I haven't used in a while. They're super creepy. You guys know, like, so what I do is I just look up fun facts about animals and then I make questions around that, right? And so platypuses, which is the plural of platypus, are super weird, kind of scary. I had to cut the test. Anyways, so yeah. Anyways, I try to keep them themed when I can. It does have to be common, so there might be some non-animal questions on there. I know, right? No, I have to convince all the other sections to all of a sudden write an animal themed test. That's what I have to do. So anyways, so like I said, the quiz is yours to keep. And today we start a new chapter, chapter 3, and confession time. I hate this chapter. I hate it. So if you don't like it, it's totally my fault because I'll be rubbing off on you. For that reason, we're just gonna kind of do the bare minimum and get out, and then we can move on to way funner stuff. I know funner is not a word, but in this case it works. So what gets confusing, I feel like I say that a lot. What gets confusing is this. Chapter 3 is called probability. Now, so here I just said, okay, I don't like probability so much, right? It's It's probably the only statistics you saw in high school, likely, right? Where, you know, you have to do combinatorics. If you pull out from a deck of cards an ace of spades, then what's the probability of this, right? So that's the probability that we're talking about here. Now we're going to talk about probabilities throughout the rest of the course, bless you, but not in this sense. Okay, so this is like a special chapter. We will be relying on probabilities later, but this is the only chapter where we explicitly talk about probability. Now, section 3.1 is quite large. It's going to take us probably today and Thursday, right? And it's where we are just defining probability. Where was it? Gonna grab from the textbook. I'll grab the section as well so you can refer to it. And draw on there so it bumps it to the top. I'll rely quite a bit on the notes in the textbook because a lot of it is just definitions, just terms that we need to be comfortable using, right? Reading, using, applying. Okay. And so first, let's talk about what is probability. Now, before we even do this, right? If I tell you I flip a coin, right? Just in your brain, what's the probability of heads? 50%, 0.5, right? Half and half. We understand that. We know how to find these probabilities. What are we assuming? We're assuming that both sides have the same probability of happening, right? And so that's why we split it evenly. It's not necessarily the case, but often we make that assumption, right? If I roll a die, right, then each side has a 1 in 6 chance of showing up, right? Because we're assuming that it's evenly distributed, right? And that's where we're going to spend most of our time, right? And then I'm going to graduate to giving you a table where, okay, so now the probabilities are not even anymore, right? So then what happens? Okay. But for now, okay, we're going to be talking about a random process. Okay, so a random process is just anything that generates some random event or an outcome. Okay, so I roll a die, that's a random process. Okay, let's see here. So these guys are a random process. And the outcomes, right, are these guys here, right? I roll a die, the possible outcomes are 1, 2, 3, 4, 5, 6, right? Let's assume it's a 6-sided die. Right? You get really, really picky about all these assumptions, right? Assuming it's a 6-sided die, sure. Like flip a coin, assuming it's a 2-sided coin. So there's always someone, well, what if it lands on its side? Yeah. We'll ignore that, right? It can happen, yes, but we're going to ignore that outcome, okay? Because otherwise it makes our problems way too difficult to solve, right? And so we do that a lot, okay? Okay, so probability, like I said, we have this intuitive understanding of the probability, okay? And so we typically look at all the possible outcomes and then we can figure out, we just split the probability of one evenly amongst those outcomes. Now, technically, what's going on is we're pretending to observe the random process an infinite number of times. Okay, so by definition, the probability of an outcome is the proportion of times the outcome would occur if we observe the random process an infinite number of times. Okay. So there's kind of common examples, right? But if I flip a coin 10 times, I don't expect exactly 5 heads and 5 tails, right? In just 10 flips, right? It's not until I've flipped it an infinite number of times that I expect to see that 50-50 show up. Turns out you can do some modeling and you can see that after 100 flips or so, it'll start to stabilize at 50-50, but it's quite volatile until then. Okay? And so, but for us, in our case, we usually assume that the probability or that each outcome is equally likely. So in our case, we usually assume each outcome is equally likely and find the probability of each outcome by taking 1 divided by the number of outcomes. Assume each outcome is equally likely and find the probability of each outcome by dividing 1 by the number of outcomes. By the number of outcomes. So for example, if I roll a die, because I don't want to, right here, I have 6 possible outcomes. We're assuming they're equally likely, right? And I'm going to stop saying that because that's kind of an assumption that we're constantly making, okay? And so don't need to say it anymore, right? Each with probability 1 in 6 or 1/6. Okay, good. So before we can do any calculations, we need some notation. Hey, I thought this was notation. Yeah, more notation. And so we're going to use probability notation just because it's going to cut down on a lot of writing. Okay, and so we often use probability notation as shorthand. You're welcome to write it out. If you don't like working with probability notation, that's fine. But I'll be using it, right? So you'll need to be able to read it, right? You don't need to be able to write it necessarily, although I think you'll gravitate towards it naturally. So I don't want to force it. You'll just do it eventually. It's taking too long to write. So how probability notation works is, I'll show you what it looks like. You use a capital P of, and then the outcome inside the brackets. So sometimes we use things that are, we can assume some understanding of the random process, right? Rolling a die is what we're talking about. So then what can I do? I could say the probability of a 2, right? Rolling a 2 is what that implies, is 1 in 6. right? And so here, this is shorthand for, right? If you wanted to write it in words, you would have to say the probability of rolling a die. You wouldn't have to say it this deep, but potentially, right? And observing a 2. Or maybe I'll even say an outcome of 2. I had to squeeze it because it's a page break. Yeah. Notice most of the time you can just kind of figure it out from kind of, I don't know, just reasonable things. Like if I asked you, what's this? What is this probability? What's the most reasonable answer? Probably 1/2, right? 0.5, 1/2, because, right, heads stands for flipping a heads in a coin. So I didn't explain that, right? But that's kind of the whole point of this probability notation is you can assume some level of kind of, oh, okay, H is for heads, T is for tails, right? You can even define it earlier, right? Let H equal flipping a heads, let T be flipping a tails, right? That kind of thing. And so, so we'll use probability notation quite a bit. Okay? And you just read it as P of 2, just like a function, F of X, right? The thing in front and then whatever's in the brackets of this, right? P of 2, P of H. Okay? Or the probability of 2, the probability of H. So here we're talking about just singular outcomes, right? What if I wanted to know, okay, what's the probability of rolling a die and rolling a 1, 2, or a 3? Right. Any one of those and I'm happy. Okay. Now what I'm talking about is a set of outcomes. Okay. And so what if we are interested in a set of outcomes? The set means that we're going to use set notation. No one likes set notation. Can't believe this. Set notation, are you serious? Are you familiar with set notation? Okay, so you use a curly bracket. I should do it nicer then. I get pretty sloppy. It's a set notation. They're hard to draw, these curly brackets, right? Usually one ends up looking better than the other, but I can't do it twice, and they're opposite. And so, and in here, so this mathematical set notation. And so now we just list the outcomes in our set inside these brackets. Probably shouldn't have finished the brackets, but I wanted you to see it, right? And so my example was 1, 2, or 3, right? Rolling a 1, 2, or 3, I don't care, right? As long as it's in that set, I'm happy. Yeah. And so this is called set notation. Right, is when you use those curly brackets. Yeah. No, so what we do, all right, here we go. We call a set of outcomes an event. Oh boy, okay. And so an event, oops. So we call a set of outcomes an event. Okay. Now, for some reason, events are typically denoted by uppercase letters starting at the beginning of the alphabet, A, B, C. And I would be totally weirded out if you told me this event is called T. What? No, you can't be serious. So for whatever reason, we just, so capital letters, beginning of the alphabet, right? Unless you have some logical reason, right, that would tell you about the information, but so we call a set of outcomes an event. An event is denoted by a capital letter from the beginning of the alphabet. You can work your way through it, but right, or that's just usually how it's done. Okay, and so if I have, so the event of rolling a 1, 2, or a 3, right, can be denoted by A, or could be denoted as A is the set of 1, 2, 3. Oh, that looks like another curly bracket there. 3 is getting out of hand. So now what we're going to do is eventually we're going to find probabilities of these events, right? I don't care which one of these, 1, 2, or 3. If something in here happened, A happened. Okay. And that can be confusing, right? Because if we're talking about, okay, what's the probability of A, then a lot of people want everything to happen, right? But if I'm only rolling a die once, only one of these things can happen, right? And so A happens, right, if any one of those outcomes happens. Okay. So here, A happens, and I say happens because when we talk about probabilities, right, what's the probability of 2 happening? What's the probability of a heads happening, right? And so A happens, right, if any one of those 3 outcomes occurs. I'll say happens again. Okay, so A happens if any one of the 3 outcomes happens. Outcomes. Hey, is it snowing? Come on. Thought we were done with that. It's freezing. Hey, at least it's not that hot in here anymore. I should have thought twice before I wore this sweater. It would be crazy hot if it was like it was before.
It was the same with Bob yesterday. The room was like not friends.
This building. If it's cold outside, it's cool in here. It's hot outside, hot in here. All right. So we distinguish between outcomes and events, but in kind of the applied world, there's no difference, right? We're going to find probabilities of outcomes or events, and the probability rules that we're about to establish, right? They're the same for outcomes of events, right? So we kind of treat outcomes and events, in fact, right, An outcome is just an event with one outcome, right? And so we treat them interchangeably. And so just a quick note, we can use outcomes and events interchangeably. Sometimes I even get sloppy and I'll call an event an outcome, and then there's outrage from you guys. That's totally fine. Try not to, but it can happen. Okay, but so from now on, we're kind of wishy-washy on what they are. And I know that that's difficult when you're first learning this stuff, okay? But just keep that in mind. Okay, so some other terminology before we get to the rules. I know you guys just want to learn the rules so you can play the game. If we have an event that's all possible outcomes, we call that a special case, and that's the sample space. Okay. And so the sample space which we denote by a capital S, so that's reserved. You're not allowed to use it for any of your other events. Okay. Notice it's a capital. It's later in the alphabet, so there's no risk of running into it, right? Also sample space. So the sample space is the list of all possible outcomes. For example, if we're rolling a die, right? So if we're rolling a die, hate to save myself some writing, I should have said flipping a coin. If we're rolling a die, then S is going to be the set of 1, 2, 3, 4, 5, 6. The first probability rule, and I never introduce it here, but maybe it's a fun place to introduce it to tie into our probability notation. The probability of the sample space is 1. Why? Because the sample space is all possible outcomes. If it's not all possible outcomes, then it is not the sample space, right? So by definition, the sample space has to include all possible outcomes. So if you roll a die, one of these things has to happen, right? And so the probability of the sample space is 1. Something in there will always happen, right? I'll follow it up with, because one thing in the sample space will always happen. When only one outcome or one event can happen, then what we say is we call those outcomes disjoint, or these events disjoint. Okay. So we'll focus on the outcomes, and then we'll quickly transition to the events. Okay. When only one outcome can happen, I guess at a time, for example, right, rolling a die. Okay. We call the outcomes disjoint. We call the outcomes disjoint. Disjoint, and I guess I should say, or mutually exclusive. Disjoint, mutually exclusive, they're just the same thing. You can use them interchangeably. I tend to use disjoint because it's more of a statistical term. However, in kind of plain speech, you've probably even said mutually exclusive at some point in your life, right? Or if someone says, oh no, they're mutually exclusive, what's your understanding? Well, you know that, okay, then those two things can never happen at the same time, right? I can't roll one die and have a 2 and a 3 at the same time. It can't happen, right? They're mutually exclusive. But I prefer to just call them disjoint. It's quicker to write, but also it's kind of statistically more proper. But you use either one, I'll know what you mean. Okay. Okie dokie. So notice here, right? I said outcome, right? But it can also be an event. Okay, so events can also be disjoint. As long as there's no overlap. Okay, so again, they can't happen at the same time, right? Which means that you can't have any overlap. So events can also be disjoint as long as there is no overlap. So these kind of tie them together with the little asterisks, right? I said outcomes, but you could easily interchange them for events. Now, for example, let's see an example here. If I tell you that the event A is 2 or a 5, and event B is a 1, 4, or a 6, I look at these outcomes, see that they have nothing in common, right? And so they are disjoint, right? So here, disjoint, no overlap.
So overlap would be like there's a 4 also in A.
Let's do that. Versus if A is 4 or 5 and B is 1, 4, 6. Right. Because if I roll a 4, right, then A happens, but also B happens, right? And so they're not disjoint. Okay. So not disjoint. Since 4 is in both sets. I told myself I wouldn't do this, but now I'm just feeling so wild and crazy. Am I feeling wild and crazy? Do I switch things up? Yeah, let's do it. Okay, so we can talk about probabilities of events, right? And so we can also talk about the probabilities of A and B. Okay? So what we're gonna say in terms of being disjoint, right? A and B, so now A and B is a new event that you've created where you combine everything in A and B, just like it says. Okay, and so we can find the probability of A and B. Yeah. Oh, this is where I probably shouldn't go rogue. I got too excited. Okay, A and B. They have to happen at the same time. Okay, and so what's the probability? So in this first, I guess I should put A1 and B1, A2 and B2. The probability of A1 and B2, what's the probability that these two happen together? 0. Why? Because I can't roll a die and end up in both events, right? It's one or the other. Okay? And we'll be able to find that probability as well. Okay, but to get there, we need to talk about the and. Okay, and so the probability of A1 and B2. Oh. Okay. Working out the kinks. I've got it. A1 and B1. B1 and B2 are the same, but doesn't matter, but it would be very confusing when you went back. Okay, so A1 and B1 is 0. Why? Because A1 and B1 are disjoint, right? And so now, knowing that they're disjoint, you also know that the probability of them happening together is 0, right? If I tell you that the probability of them happening together is 0, they're disjoint, right? So you've got this kind of chain. Okay? Because A1 and B1 are disjoint. We're going to rely on that a lot, right? That kind of connection. Okay? We might be in over our heads here, but the probability of A2 and B2, how about for now, can I just say it's not 0? Yeah, okay, cool. Right, it would be some number and it's okay, we'll get there, but I don't wanna overwhelm the process here. Okay. Since they are not disjoint, or they are, yeah, not disjoint. Yes.
So yeah, it's not gonna be 0 because there is one case.
Yeah.
Where it can be.
Yeah.
true.
So since 4 can happen, right? Well, we can talk about it, right? What's the probability of rolling a 4? 1 in 6. So what's the probability of A2 and B2? 1 in 6, right? Because that's the only time that I can have both A and B. Do you guys want me to write 1 in 6 or do you prefer the not 0? Not 0. Let's say specifically the probability of A2 and B2 is 1 in 6. There was a second question, I feel like.
Yeah, so would that change, say, that wouldn't change if you put all the numbers in, so let's say A2 had 2 and 3 as well.
It would.
Still be 1 in 6, but if you put. it wouldn't.
So it depends on what the overlap is. So here it's very specific to 4, but if I had 5 in here,
Yeah,
then it would be 1 in 6 plus 1 and 6, but we haven't learned that skill yet. So that's why I had to rein it in. So, but it is exactly what you think it is, right? 1 and 6 plus 1 and 6. But for now, let's just leave this here and just explain, because A2 and B2 are not disjoint. Right. 4 is in both. Right, so if I roll a 4, then A2 and B2 are satisfied. All right, I'll just say that if I roll a 4, A2 and B2 are satisfied. Okay. So this is where I'm trying something just crazy. Law, large numbers, blah, 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 all things we should be talking about probably. Like I said, get in, get out. I'll only teach you what you need for the final. We've got better things to do. Okay, so they're using A1 or A2, right? But I actually don't want to talk about this special case. So it's called the addition rule of disjoint outcomes. What I want to jump to is just the general addition rule, okay? Because this is where I'm trying to be so hip and happening. Where is it? Okay. Put it on a fresh page here. Okay. So the general addition rule says, if A and B are any two events, and we're going to talk about generic A and B a lot, right? On your formula sheet, you'll just have a generic A and B. And so you'll need to map that to specific events, but we'll get there. So if A and B are any two events, disjoint or not, then the probability that at least one of them will occur is the probability of A or B, right? So now, at least if one of these things happens, right? If either A or B happens, then I want to find the probability of that. Okay. It's going to be the probability of A plus the probability of B minus that overlap. Okay. And so the probability of A and B. Now the special case, note, if A and B are disjoint, the probability of A and B is 0. And that's where we get the special case of disjoint events. But I wanted to introduce this, this general addition rule first, because a lot of the time when I introduce the special case for disjoint events, people forget about the general rule when it's always the general rule you should be using. Okay. And then just remember that, and we're going to pick this apart, right? So don't worry about that. Right, I just wanted to get to the subtracting of the probability of A and B, and then just remember that, okay, if they're disjoint, if they can never happen together, then it's 0. Right? So you don't need a different rule, you can just use this general rule. Okay. Now, let's take it back a step. Okay. So first, let's focus on when they are disjoint, right? That's kind of the beginner case. And then we'll graduate to when they're not disjoint, right? But either way, we're gonna use this formula. So let's say we have disjoint events. Okay. So let's say I want to find, and maybe I should say outcomes here, but notice that I've just started saying events for everything, right? And that's totally fine if you do too. But let's say I want to find the probability of rolling a 2 or a 5. Right? It's implied that I'm rolling a die here, and I want to find the probability of a 2 or a 5. So now, just this is all we have so far, right? I haven't told you anything else. So, okay, I can map this back to this general addition rule, right? The probability of wherever I see an A, I'm going to replace it with a 2, and wherever I see a B, I'm going to replace it with a 5. Right? And so here I have, I'll write below it, A or B is the probability of A plus the probability of B minus the probability of A and B. Okay, so here, right, wherever I see an A, I'm going to make it a 2, and wherever I see a B, I'm going to make it a 5. And this is where it can get super boggy if event A is denoted by a B because it makes more sense, right? And B is denoted by something else. But anyways, you just got to map it back. So then we get the probability of 2 plus the probability of 5 minus the probability of 2 and 5. Right. Okay. The probability of rolling a 2, right? We know 1 in 6. So here, I guess I should have written these in top-down order. You know what? I'm going to start fresh here. So probability of 2 or 5 is the probability of 2 plus the probability of 5 minus the overlap of 2 and 5. I'll just say, so we want to find this. Now, 1 in 6 plus 1 in 6. Okay. Usually we will know these probabilities. Minus 0 because 2 and 5 are disjoint. They can never happen. If I roll a die, I can only get a 2, or a 5, I can't get both, right? And so here, this is since 2 and 5 are disjoint, right? Can never happen together. On one roll, I guess that's important. Okay, so then here I'm dealing with fractions, of course, 1 in 6, 1 in 6. Luckily, I have a common denominator, so I get what? 2 and 6. Minus 0. So the probability of rolling a 2 or a 5 is 2 in 6. Okay, yeah.
You wouldn't,
You can make,
No.
I don't, no. That's where I stray from it being a math course. Now I can't think of the word. I don't simplify. I rarely simplify, right? Unless, in this case, it's relatively obvious, but it's not something I'm expecting. Often we'll convert it to a decimal, right? Use the decimal approximation, okay? But for us, that's where I get a little lazy on the math front, right? I'm allowed to, it's statistics. All right, so let's see here. Let's see here. How about what about if they're not disjoint? So instead of beating not disjoint events, instead of beating this poor die example to death, let's bring in our second most favorite scenario, a deck of cards. Okay. There are lots of questions that we can ask about a deck of cards, and usually I get people telling me, well, I don't know about a deck of cards. Well, here it is. This is what it looks like, right? And so there are some key features of a deck of cards that we have to keep in mind, but I'm not going to ask you anything crazy, right? I don't know any of the names of a hand, for example, right? Well, I know full house, but I don't know what it means. I think it's 3 of one and 2 of the other, or 2 of something else, I think. Anyways, so I don't know that, but here are the key pieces of information that we need to know about a deck of cards, okay? So, key deck of cards. Oops. Information. Number 1, there are 51 cards in a deck. I know. Just seeing if you're paying attention. There's 52 cards in a deck. It's here too. You guys are on top of it. There are 52 cards total. That's important. What does that mean? It means that the probability of drawing any one card is 1 in 52, right? So, okay, great start. Let me just see, no, I kind of cut that in my new and potentially improved way of approaching it. Potentially, we'll see. What's another thing? There are 4 suits, okay? And so each of these is called a suit. There are 4 suits. And let's see if I can remember. I always want to call the first one clover, but it's not. It's a club, I think. Right? Yeah. I'm relying on you guys. So a club looks like this. I stick to the ones I know, the diamonds. The heart I don't need to copy it, I guess, but. And finally, the spade, I think. Ah. Okay. There are 13 cards in each suit. Think, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13. Phew. I don't know why in this case they put the ace at the end. It'd be nicer looking if it was at the beginning, but this is from the textbook, so I didn't want to change it. But I would probably have moved the aces to the front and call them ones. Just makes it look nicer. Sometimes aces are high, sometimes they're low. That's beyond us. Or maybe it's starting to feel familiar. I don't know. We then have 3 face cards. Okay. So Jack, right? Okay, there's a Jack, a Queen, and a King. Man, rough. Each suit has 3 face cards. Jack, Queen, King. Any other kind of crucial information that we need? Probably not right now. Okay, so that's just things you need to know about a deck of cards. Because what can I ask you? I could ask you, what's the probability of drawing a Jack? It helps to have the image, right? 4, because there are 4 Jacks, right? 4 over 52, right? Because it's all of them. This should feel familiar, right? From those tables that we were looking at the end of chapter 2, right? And those, we were talking about probabilities, we called them proportions or percentages, but probabilities are just proportions and percentages. Okay, so let's see here. So for example, the probability of a Jack, we said was 4 over 52. And I don't spend any time reducing that or anything, right? I would suggest getting a fun calculator like this one, because it just reduces it for you if it can. So 4 over 52 reduces to 1 in 13. Right? I'm not expecting that, but it's nice to have. So I recommend this calculator. It also does some derivatives, I guess, and some integrals, but yes.
Is it expected that we keep it in fraction form or like more in a percentage?
Well, for me, if I'm marking it, I don't really care. I'll be on the lookout for either. And so if you're done at 4 over 52, that's totally fine. If you prefer to see it as a decimal, that's fine too. I might tell you, give it in decimal form, round it to 4 decimal places or something like that. Then you should follow those steps. But in terms of the assignment, it should be able to handle both or either or.
But is there like a good?
If you're yes. If you're using it in future calculations, you should keep it as a fraction, right? Because anytime you're rounding, you're basically stunting your future numbers, right? And so you're throwing yourself off a little bit every time you do any rounding, right? So that's generally bad, but so you're using it for later, I would keep it as a fraction for as long as you can. That said, dealing with fractions is kind of annoying. Common denominators and all that jazz. Okay, so what if I let H is the event of drawing a heart. So notice how now I'm using a letter that corresponds to what I'm talking about, right? It's just when you're making up events, you start at A, B, C, etc. Okay, and so let H be drawing a heart. And I'm going to let F be drawing a face card. Okay. We can start itty bitty, right? What's the probability of H? So the probability of H, you can even go and look at this here, right? And so all of these are hearts. So you're just looking at what satisfies the heart criteria. And then you see if you count, there's 13, or this is where it comes in handy to know that there are 13 cards in each suit, right? Either way, however you get there is totally fine. No style points. So 13 over 52. Let's find the probability of a face card. Okie dokie, artichokey. I've got 3 in each suit. Knowing that there are 4 suits, I have 12 face cards. All right. So 12 over 52. What's the probability of H or F? Now I don't care if I'm drawing a heart or a face card, as long as it's one of those, then I'm happy. Okay, so yeah, of course you could look back here and you could say, okay, well, I know there's 13 here of the hearts, right? And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 face cards. But what did I just do? What was the problem exactly is this overlap. I just counted these 3 cards, the heart face cards twice, right? And so I'm gonna grab this so we can draw on it. Oh, hello. Doesn't wanna, now it's probably gonna paste twice, but whatever. Okay. So here I want the probability of a heart or a face card. Okay. But here's where we need to be extra careful, right? We've counted these 2 cards or these 3 cards twice. We don't want to count these 3 cards twice. So if we map just this general equation from that general addition rule that we had, right? The probability of A or B is the probability of A plus the probability of B minus the probability of A and B, which, buckle up, probability of H plus the probability of F minus the probability of H and F. So I've done that mapping. that's going to take some practice, right? I'm not expecting you to go straight into it and just say, oh yeah, I know how to map it to that formula, right? But I do, and we're speeding things along here, right? And so here, this subtracts that overlap, right? And I guess I should include the subtraction, right? Subtract the overlap. Visually, right? If we weren't talking about two things that had overlap, that's by definition, they're disjoint, right? So if there's no overlap, you subtract 0, right? And so here, if there is overlap, then we need to take that into account, okay? So the probability of being in this overlap, there are 3 things out of 52, so that probability is 3 in 52. So I can start fresh here. The probability of H or F is the probability of H plus the probability of F minus the probability of H and F. We said the probability of H was 13 in 52. The probability of F was 12 in 52 minus the overlap, which is 3 in 52. Common denominator, that's nice. 13 plus 12 minus 3 all over 52. So 22 over 52. Now, just in case, when you're doing, because this is the first assignment where it's, it's the real deal, and you'll have to kind of navigate my Okanagan math for potentially the first time. I did post those other assignments that you can do, but I'm also dropping your lowest 3 assignments, I think, in case you don't feel like doing them. Might be a good idea to do them though, because they're going to be easy marks now, right? And then you can have some other ones later drop, but that's up to you. Okay, and so it might ask for the exact probability, right? And so the exact value is this fraction or this fraction reduced, if that applies, but I'm just gonna, so this is the exact probability. Or as a decimal, it's approximately 0.42308. I'm trusting my past self. Okay, so I did round a little bit, but that's okay. It's unlike me, but it's been lazy. I did the approximately, so it's approximate. Okay, so that's how we're going to find probabilities of event A or B, right? You just need to remember that if there's overlap, then you need to subtract that once. Yeah. One thing that I want to show you before we drop this and continue next day is it might be helpful to use a Venn diagram. Okay. So to solve these problems, I find that it's quite useful to use a Venn diagram. So to help organize information, we can use a Venn diagram. Organize information. We can use a Venn diagram. So a Venn diagram, you've probably seen, they're excellent for jokes. Right? I think I had one where it was like people who do CrossFit, people who go to Burning Man, and something else. And then in the middle, it was people who can't stop talking. What does that mean? It means that if you do all those 3 things, you can't stop talking. Okay. I'll try to dig it up for next day, but anyways. Sorry if you go to Burning Man. And do CrossFit and do whatever the third thing was. Might be hurt. Or maybe you can't stop talking. All right. So here's a 2-event Venn diagram. Okay, so for 2 events, in this case, we can talk about the hearts and the face cards. Okay. Which means that this overlap area here is where it's both a heart and a face card. Okay. So this is where there's H and F. So everything in the H circle, right, including that overlap, it's still a heart, right? But 3 of those are special because they're in both categories, right? So here I have a count of 3. So this whole circle right, is all the hearts. And we know there are 13, right? But usually what we do is we're only truly interested in kind of this area. So because we've already looked at that overlap, so you start in the center and then you kind of onion your way out. Okay. And so here we have 13 minus 3 is 10. And I know why. It looks like a half moon, but I can't think of any other way to describe it. So usually if you're texting me questions or asking me questions, then I'll talk about the half moon, right? Because most of the time the question is, well, I can't get the right numbers, but you have forgotten to take away that overlap, right? So 10 are in the half moon area. Which means what? They're they're hearts and not face cards, right? Because they're not in that overlap. Same thing on the other side, right? Of course, these 3 are also face cards, but they're special face cards, right? And so what we're going to be talking about mostly are these guys. Right, which is, so there were 12 face cards, but 3 are in the overlap, so there are 9 face cards that are not hearts, which you can count and check, right? 9 face cards that are not hearts. We haven't addressed this this rectangle. It's everything keeping everything under control. And so what that rectangle is kind of symbolizing is the sample space, right? We know that there are cards that are not hearts and not face cards, and they are just floating around in the rest of the sample space outside of this area. Okay, and so this here is the sample space. Right, all possible outcomes. Like everything we do, it's going to take practice translating a question into a Venn diagram. We can also go into 3 events, which would, just so you know what it looks like, because you might need it. Hint, hint. Oops, I got sloppy. Okay. When you're filling this in, start start in the center and work your way out. Right, subtracting the values that you've already seen. Okay, and so what I'm gonna do is I'm gonna post an assignment called Defining Probability 1, where you'll get to practice, right, making Venn diagrams, because we're all out of time in 1 minute. Potato, potato. So I'll give you some practice there that you can try out. And then we'll continue this section on Thursday. If you didn't grab your quiz yet, you can grab it. And if you have any questions, let me know. Otherwise, I'll see you on Thursday.